Hello all. Today before we jump straight into notes, I want us to actually look at some concrete examples for series. So pause this video, take a look at these first two questions on there and see if you can get a sense of whether these converge or diverge and if there's a common ratio. And I know we could also write this sequence right here with my starting value, and then I know I'm multiplying 2 after that however many times to get to 10. And so I could actually write this as a geometric series like this, and then know that this is my common ratio. Well, it's bigger than 1, so it's going to diverge. I'm going to try that with number 2. Already with number 2, I'm a little perplexed because they're not exactly, I don't know what I could multiply by, so I could do a little quick math over here. If I multiply this by something, my common ratio to get 192, then I could actually solve out for what that R value is, what I have to multiply by, and it looks like that's a crazy number. It actually ends up being 3/4. So what I can multiply by each time, and you can check this out, it's a multiplication of 3/4, so times 3/4. And I can even write this as a geometric, but we can already kind of tell since the ratio is 3/4 and that is less than 1, I'm going to assume this is going to converge geometrically. And again, I could even write this as a geometric series here with my starting value, and then I multiply by 3/4 n many times, so I've multiplied by 3/4 twice to get to my third term in my sequence, which will be n equals 2. Yep, so that works. I can even tell you what this actually converges to. Geometric series are awesome because I can do 1 minus my ratio, so 1 minus 3/4 on the bottom, and then here is my a value, so 256 is my a value up on top. And if I do that math, this will actually converge to 1024. So if I try to do this same kind of thing with a series that's a little bit funkier, so a sequence of 1 over n factorial, I can actually start to fill in this value. So it's going to be 1 over 3 factorial, which will be 1/6, 3 times 2 times 1. This will be 1 over 24. And I look at my, well, it's not a common ratio, but I look at my ratio that's actually occurring here. This is getting multiplied by 1/4. This is getting multiplied by 1/5. If I look at these values over here, this is getting multiplied by 1/15 to actually get that extra value. So if this is 1 over n factorial, then I'm actually multiplying by 1 over n plus 1 to get my 1 over n plus 1 factorial term right there. So that's actually kind of what our ratio is going to be. This is our ratio. And it's not a common ratio because it's not, always the same. No common ratio there. It's not the same. It's changed each time. But each one of those ratios is actually less than 1. So we can already say that this is going to converge via the geometric series. My thing that I did up here where I took a term and I multiplied by that ratio to get the next term, we ended up with our our second term over our first term, which is another way of kind of saying our nth plus 1 term divided by the term right before it, in this case, gave us a ratio of 3/4. Down here, if I did that same thing, so I took my nth plus 1 term over my a sub n term, that would actually give me the ratio of 1 over n plus 1. Probably, but I actually want to, I'm gonna do this on my next page. So if I actually try to write my nth plus 1 term in my sequence, I'm gonna put that on top. So n plus 1 is inside of my factorial all over 1 over n factorial. And I know that this looks weird, but we can actually multiply by our reciprocal on the bottom right there. And this will actually simplify down to 1 over n plus 1 factorial times n factorial on top. It seems like that would be the most reduced down that we could have, but I want to remind us, so n factorial is the same thing as n times all of the terms that are less than that. So one term less than n is n minus 1. Two terms less than n is n minus 2. And this just keeps on going down forever until I get to 1 and then I stop. Well, my n plus 1 factorial starts with n plus 1, and then again I multiply everything that is less than. So n plus 1 minus 1 is just n, and then 1 less than n is n minus 1. And you can probably start to see a pattern that happened here. All of these terms will actually end up canceling out, and I will just get a 1 over n plus 1. So that, again, was our ratio that we found above. And as we go further and further out, so as n gets bigger and bigger, that's another way of saying as n approaches infinity, so we take our limit as n approaches infinity, this is going to go to 0. So this should converge since that is less than 1. And I'm getting that 1 from our geometric. So this is actually our ratio test for convergence, and it's tying together these ideas of geometric series, and then also if I take my nth plus 1 divide by my term right before it, I can look and see, hey, is that going to be less than 1? So geometrically that would converge. My ratio is getting smaller over time. Is my ratio getting bigger over time? And that's when we would have something that diverges. And if it equals 1, then it's inconclusive. We would want to use another test for that. So that was an activity that we actually did in class. And that was a great introduction into ratio tests themselves. Like, where does this actually come from? So I'm taking my term, my nth plus 1 term, dividing by my nth term right before. The absolute value part is again geometric. I don't care whether this is positive or negative, so I can take my absolute value of that. And then my limit as n is approaching infinity, I go way far out in my sequence. If my ratio is getting smaller over time, my limit should be something that is 0 or less than 1. If it's bigger, it's going to diverge. If it's equal to 1, then I can't use that test and I should try using another one. I want to actually look at this example right here, which, again, if we're using a ratio test, I'm going to start out with my a sub n term is on bottom and my a sub n plus 1. So the top one is where I add 1. So I'm just going to write 2 to the nth power over n factorial, and that's going to be on the bottom. And then my a sub n plus 1 is going to be up here on top. So I'll have 2 to the n plus 1. My plus 1 goes in with the n. And then down here for my factorial, my plus 1 is going on the inside of that. And this is what I am looking at, my limit as n approaches infinity. I could put some absolute value bars here, but it's not really going to make any difference because I don't have any negative terms. So I am really looking at multiplying by the reciprocal here on the denominator to cancel that out. So I'll end up having something like this when I multiply that reciprocal also on the top. I'll have an n factorial over 2n. And it feels like we can't really do much after that, except that if I take a look at this right here, and I'm actually just going to write this in a slightly different format. If I had like 2 to the 3 plus 1, I know that I could combine those to be 2 to the 4th. But another way that I could actually write it is I could write it as 2 to the 3rd times 2. So that 1 is like my exponent here, that 3 is like my exponent here. And I can do that same thing with this 2 to the n plus 1. I can rewrite that as 2 to the n times 2. So that plus 1, I kind of peel it off, and I'm just left over with 2 to the n times 2 all over. I'm going to do the same thing with my 2 to the n down here. Oh, and actually those things should be able to cancel out. That's amazing. Now I just have to kind of worry about my factorials and what's happening there. So as we saw in that example right before this, a factorial, I'm multiplying all of my terms that are less than that. So 1 less than n plus 1 is going to be n. And I'm going to multiply all the things that are less than n. So essentially I will have an n factorial right there. I just peeled off an n plus 1. And you can hopefully start to see that those will cancel out, and I will be left with my limit as n is approaching infinity of 2 over n plus 1. And sure enough, n, my denominator is getting huge, so I'm going to have 1 over something huge. This will actually equal 0, which is less than 1, which means that this not only converges, but it absolutely converges. I want to take a look at 2 more of those ratio tests that I would have here, and how we can kind of do that peeling off of terms that we have. So I'm going to go ahead and get this set up. My exact sequence term goes on the bottom, and then my n plus 1 term is going to go on top. So I'm going to have n plus 1 factorial over, and then this is an n plus 1 raised to the now n plus 1. This is what I'm going to be taking my limit as n approaches infinity. I'm going to go ahead and multiply by the reciprocal on the bottom and see if I can reduce some things down. Now that I have that written down, I'm going to start peeling some things off. So the thing I'm going to start with is this n plus 1 factorial. I can write that as n plus 1 times n minus 1 times n minus 2. Or I'll just leave it as, I'll peel off just one of those terms and leave the n factorial right after. So now I can actually see that those 2 terms will end up canceling out. And I'm going to do the same thing with this n plus 1 raised to the n plus 1 power. So I'm going to write this as n plus 1 to the n, and then times n plus 1 raised to the 1. So as long as these things are multiplied, they have the same base, I can add them together into n plus 1. We're not used to actually doing the opposite direction. It feels kind of weird. So I'm going to cancel the things out that can be canceled and rewrite those remaining terms. I have my n plus 1s both cancel out right here, and I'll actually just be left with my limit as n approaches infinity of n to the n over n plus 1 to the n. And these are both tower functions. They're kind of funky. We're back to doing stuff with limits. And so one of the most common useful things to use in limits is L'Hopital's. We just have to make sure that this is in inconsistent form. So in L'Hopital's, if it's infinity over infinity, which is sure enough exactly what this is, or if it's in indeterminate form like 0 over 0, anything like that, we can take the derivative of the top and the derivative of the bottom separately. And so how I would go about doing that is I would take my derivative of n to the n, so my n can come out in front, and I'll be left with n to the 1 less than n. So n to the n minus 1. That's the derivative of my top, and my derivative of my bottom. Very similar thing is going to happen. That n is going to multiply, and then I will have n plus 1 now raised to the 1 less than n, so n minus 1. And we can see that we're going to kind of be in this almost loop where I could just keep on doing this until and get smaller and smaller and smaller. So I'm going to do it just one more time. This n minus 1 is going to come out in front, and I'm going to be left with n raised to the now 1 less than n minus 1, so n minus 2. And then over here, same exact thing. It's still in indeterminate form, so I can take my derivative. My n minus 1 will be multiplied by n plus 1, now raised to the n minus 2. And if I do this n many times, so I just keep on doing this, dot, 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 I will eventually get down to where I'm looking at my limit as, and let's just substitute in 3 for this. So if I substitute in 3 for my n, by the way, those cancel out. If I substitute in 3 for my n, I'll be left with 3 to the first power over, let's see, 4 also to the first power. And if I do this, that was when n equals 3. If I did this for when n equals 2, I'd be looking at, let's see, 2 to the 0 power over, and then this would be 3 to the 0 power. So my ratios are actually decreasing. My limit of these values as n gets larger and larger and larger is actually going to go to 0. And even both of these values right here are, the ratios are less than 1, so this one is going to converge. The last question that we are going to look at when it comes to the ratio test is this value here. Let me get it set up. Okay, so I have my a sub n term written right below, and now I'm going to look at my a sub n plus 1. So we have to be very, very careful. We're actually changing that n right there to be a plus 1, but it's inside attached to the 2, and then we have the factorial on the outside. So I'm going to have to distribute that 2 into the n and to the 1 before I actually look at the factorial of it. Same thing for down here. So I'm going to have an n plus 1. I'm replacing that n with an n plus 1 factorial, and then that's what's being squared. I'm going to multiply by the reciprocal on the bottom. Let's rewrite that. And now I'm going to start that kind of pattern or way of thinking where we peel some of these values apart to see what can cancel out. So this 2n plus 2 factorial means that I can start with my 2n plus 2 term and multiply by 1 less than that, which would be 2n plus 1, and I can multiply that by 1 less than that. So I'm just looking at the definition of a factorial, and I could just keep on doing this, like 2n minus 1 times 2n minus 2. But I'm actually just going to stop right here because you may see on this side I have a 2n factorial on the denominator, and I want to be able to actually cancel those out. Let's try that with this n plus 1 factorial, which is going to be n plus 1 times, and I'm going to leave this as just 1 less than n plus 1 is just n factorial right there. And both of these terms are actually being squared, which if I had like a 3 times a 4 squared, that's the same thing as if I had a 3 squared times a 4 squared. So over here I can rewrite that denominator part as n plus 1 squared over n factorial squared, and then now I should be able to cancel some things out. And so now we're back to kind of just looking at limits here. I'm actually going to multiply all these things out. I could also use L'Hopital's rule here because I technically do have infinity over infinity, but I want us to actually just see these as polynomials and just as actually cubics in this case. So if I multiplied all of these out and I multiplied my n plus 1 squared, which, remember, doesn't just have an n squared and a plus 1, but also an n times a 1 and then another 1 times an n, so it has that middle term. You can see that the degree of the numerator and the denominator are both 2, and thinking back to pre-calc, another way of thinking about limits is horizontal asymptotes. So this rational function would have a horizontal asymptote at, since it's the same degree on the top and the bottom, the leading coefficients. And there's really kind of a leading coefficient of 1. So my horizontal asymptote here is at 4 over 1. That is also going to be what my limit actually approaches. It approaches 4. Since 4 is really big, well, it's bigger than 1, this is going to diverge by our ratio test. If I look at both of these questions, so my harmonic and my one that I know converges because of p-tests, if I try to use a ratio test on both of these, I actually end up getting that my ratio is equal to 1, and so it's inconclusive, and we would want to use a different test. So both of the ratios equal to 1 gives us inconclusive tests. There's no information. We're going to look at one last test. And this very last test is actually really similar to the ratio test in that we can kind of relate it to geometric series. So I want to take a look at an example right here, which I could also rewrite this series as 2 over n raised to the nth power. And as long as, if I'm thinking about this geometrically, as long as 2 over n, the ratios between all my terms are less than 1, so geometrically, and another way of saying that is as I go further and further out, or I take my limit as n approaches infinity, then we are good. So I'm already assuming that this is going to be fine because my limit of 2 over n is just going to be 0. But we're going to do the ratio test on this. So ratio test looks like I'm taking my nth root of these terms. And so since they both have a nth root in their exponent, I can actually cancel that nth root out right there. I technically should have an absolute value, but both of these values are positive, so I don't really need an absolute value there. And sure enough, we can actually see this equals 0. That is less than 1, so this is going to converge via the root test. And that is exactly what our root test is saying up here. So if our ratio is less than 1, it converges. If it's greater than 1 or infinity, it diverges. And then if it's equal to 1, we don't know. We have to try a different test. Ratio test is also really, really useful when we have n's in our exponent. So already I know I can kind of write this as just something raised to the n power, and that something raised to the n power would be my n factorial and then n squared here on the denominator. So I'm separating the 2n and bringing the n kind of out in front. So why that is helpful is now when I actually do my root test, which is taking the nth root here, and those two things cancel out, I'm really just thinking to myself, well, what's getting bigger faster, n factorial or n squared? And my n factorial is definitely going to win out in this situation, but we have a couple tricks up our sleeves when it comes to limits, and that is if we have something like this, we can technically do L'Hopital's rule on it. But I just want to think if n is even, I don't know, 100, I would have 100 factorial, which means I'd have 100 times 99 times 98, all of those numbers. And then here I would just have 100 times itself, or 100 squared. This is going to get freaking huge. So my limit here is actually infinite, and this is going to diverge. Okay, last part, because this is the end of our chapter. Like, we have learned all of the tests. I have a flowchart at the very, very end of this. So I don't know why, but I find this flowchart very, very helpful. It has a toolbox, so things that we should be able to recognize, and then tests that we should be able to determine. If you take this, if you had looked at this flowchart at the very beginning of the class, you would have been like, what? But all of these things on here, we've gone over, and hopefully they're starting to make more sense. So I want you to read these. Choosing a convergence test for a series is really, really helpful. That flowchart at the end is helpful. But I also want to just demonstrate what might be the best test, and then I'm going to make some mistakes on purpose because what might be the best test maybe won't always work. And so when I look at this first one, I immediately want to compare it. Let's try something. At first, when I tried to do this one, I wanted to try to compare it with something that either I knew converged or diverged. So if I compare this to n squared plus 1 over n to the third, so my denominator is larger over here, which means that when I divide by it, it's actually going to be smaller than. And then this term over here, I would have like n squared over n to the third. Well, that's harmonic, so that diverges. And I would also have 1 over n to the third that converges, but my divergent takes over. I don't really care that I found something that is divergent here, but I have something I'm trying to compare it to that's less than it. It doesn't make sense. I would want that something that I'm comparing it to be larger than. So my comparison test right here just didn't really work out. I was still kind of on the track to try to compare this to something, so then I thought, well, what if I try to compare it to, like, if I keep the denominator the same and then I just have n squared right there? And so how does this term over here compare to that one? Well, it's probably going to be bigger than or equal to for very, very large values of n. And what do I know about this term over here, or this sequence? And I actually know that this term converges. So having something larger than it isn't actually going to help me at all. So once again, a direct comparison test did not help. My next idea is to actually do a ratio of my limits. So I'm going to look at my limit comparison test and we'll try that. So what I'm going to do is I'm going to take my top part, and I'm going to compare it to something that I either know for sure converges or for sure diverges. And since our ratio between the degree at the top and the bottom is 1 over n and 1 over n diverges, I'm actually going to try that. So I'm going to do 1 over n. And this is my limit comparison test. So I need to take my limit as n approaches infinity. If I actually simplify this out and I multiply by 1 over n, I will end up getting n squared plus 1 times n over n to the third power plus 2n. And you can see that there are 2 n's on my denominator here, so I can actually cancel that n out with an n in both of those terms below. And I'd be left with n squared plus 1 over n squared plus 2. And we can see that both of these have the same degree on top and bottom, so I can compare my ratios. Look at the horizontal asymptote. This is going to equal to 1, which is not 0. So by the by the limit comparison test, since this thing is divergent, then this is also going to be divergent. I just want to say that it is okay to like try things and then see if they make sense, and if they don't, try something different. Like automatically on this one, because of that -1 that's right there, I want to try the alternating series test. And so the conditions that have to be met, it has to be decreasing, which in this case, I'm looking at n to the third over n factorial. That's not decreasing. At least for the first few values, it's not decreasing. So I can't actually use my alternating series test here. But I still have that factorial, and so factorials are really nice when it comes to either my ratio test or my root test. Actually, ratio test is even better because I can kind of peel those off and I don't have any n's in my exponent here, so maybe root test isn't the way to go. I'm going to do ratio. And my absolute value part here is actually really helpful because it doesn't really matter. This -1 to the n plus 1 doesn't really make an impact anywhere, because if it was negative, I would just have the absolute value. If it's positive, then it would just be the same thing. So I just left that part out, and I'm just looking for this limit as n approaches infinity. I'm going to go ahead and multiply by that reciprocal on the... Okay, I'm going to go ahead and peel apart this n plus 1 factorial that's on the bottom. So I'm going to have n plus 1 times n minus 1, or I'll just have n factorial here. Then I can cancel out those n factorials. So I'm left with my limit as n is approaching infinity of n plus 1 to the third power all over n plus 1 times n to the third power. So the degree on my top is 3, the degree on my bottom is 4. My denominator is getting bigger faster, and so this is actually going to approach 0. And I just showed, since that's less than 1, that this converges. Yay! So the weird thing is that I'm demonstrating how to actually mess up on stuff, which is okay, as long as I could just keep on trying other tests. So on this next one, I was almost thinking that I could do another limit comparison test. So like e to the n over n to the third, if I try to compare that to something that I either know converges or diverges, I try to do e to the n because I know that that for sure diverges. Geometrically, since my base is bigger than 1. But the second that I tried to do that, I ended up getting 1 over n to the third, which I know that actually converges, or my limit of this approaches 0 because my denominator is so big, and that doesn't actually tell me anything. That doesn't tell me if this top one converges or diverges. So then I started to think, oh, well, if I'm thinking that this might diverge, which my numerator is huge compared to this n to the third, then why don't I just use my divergence test? So my divergence test just tells me if I take my direct limit and my direct limit does not approach 0, then it doesn't diverge. And sure enough, this actually is infinite, which is definitely not 0, so this is for sure going to diverge. Okay, by the time I got to the fourth problem, I was like, you know what, I'm okay, I'm resigned to possibly messing up because then I'll just try a different test. But I saw this n in my exponent, so I was like, oh, I might as well try a root test. So I tried that and it ended up working because my n's canceled out. I'm looking at my limit as n is approaching infinity, and I end up getting my limit as n is approaching infinity of 3 over n plus 1, and sure enough, that does equal 0, which is less than 1. So by the root test, this does converge. Let's take a look at some of your practice or your homework. Okay, on these next pages, I have these on your formula sheet, so you can also write them down, but they are also on your formula sheet. We have gone through all of these tests. Here is the flowchart, and then we have our practice problems. Okay, so there are 3 on this page, 3 on the next page. I will tell you right now that I found that 4 of these converge and then 2 diverge, so that's a little hint that I have. Also, another little hint is that this terminology down here is not trying to confuse you. You can really just write that series right there as n equals 1 to infinity of 3n minus 2 over 3 to the n factorial. So that's another way that we can actually write that. My last hint is for this second one right here. To try and use not the limit or the ratio or the root test, anything like that, but just to try to use a test that you might use if you're trying to show that it diverges. So that is my hint on this A1. You might also have to use L'Hopital's multiple times, kind of like we did before in that example.